Hello everyone, this is Maria Charisi. I'm a postdoctoral fellow at Vanderbilt University, and today I'm going to talk about this paper that I led on behalf of the Nanograph collaboration using the most recent dataset to place constraints on supermassive black hole binaries in nearby galaxies. First of all, supermassive black hole binaries are a natural expectation of galaxy mergers, since every massive galaxy hosts a supermassive black hole. As the merger progresses, the two black holes come together, and at very small separations, they become the most promising sources of low frequency gravitational waves. And at the most massive end of the supermassive black hole binaries, these gravitational waves are in the nanohertz regime and can be detected by pulsar timing arrays. So pulsar timing arrays use the most stable clocks in the universe. And what happens is we have a galaxy merger somewhere in the universe, preferably in the nearby universe. We have gravitational waves passing through our own galaxy, and they squeeze and stretch the space-time, which means that they squeeze and stretch the distance between the pulsars in the galaxy and the Earth. That means that some of the pulses will come faster, some pulses will come slower. And using this technique, if we detect this signature in multiple pulsars, we can detect gravitational waves. There are two main signals that PTAs will detect. One is the gravitational wave background from the superposition of many binaries, and gravitational waves from individual sources, which is the target of this talk. Of course, as you know, we haven't detected gravitational waves with pulsar timing arrays, but we can use the current data to place constraints on the gravitational wave strain of tentative binaries. And here you can see the constraints on the gravitational wave strain for individual sources, the sky map from the 11-year dataset of Nanograph. With stars, you can see the location of the pulsars. And as you can see, at the part of the sky that we have more pulsars, we can place more stringent constraints. So what I wanted to do in this paper was to use this map and the information we have with the most recent data set and apply it to specific galaxies that Nanograph could probe. So the first step for that is to build a catalog and find all the galaxies that if they hosted a binary, Nanograph could detect gravitational waves from those galaxies. So I used the two-mass spectroscopic survey, which has the three-dimensional position of 45,000 galaxies. So I calculated the distance and the mass of the central black hole for each of these 45,000 galaxies. And then I populated them with binaries at the most optimistic scenario for detection. So I populated them with circular binaries, equal mass, emitting at 8 nanohertz, which is the most sensitive frequency that Nanograph can probe. And then comparing them with the sensitivity map I was showing at the previous slide, I can find which of those galaxies would produce detectable gravitational waves. The galaxies are shown here. They are color coded with the distance, and the size of the dot shows the mass of the supermassive black hole. As you can see, we are sensitive to binaries that are between 10 to the 9 to 10 to the 10 solar masses, and in a sphere, not really a sphere, in a volume that spans out to 500 megaparsec. So what we did was to estimate the gravitational wave upper limit, the strain upper limit, which quantifies the squeezing and stretching of space-time as a function of frequency for each individual galaxy. And here I'm showing just one example. So from the pulsar timing analysis, data analysis, we have these constraints on the gravitational wave upper limit. And then using this relationship here and the distance that I have calculated for each of these galaxies, I can place constraints on the chirp mass, again as a function of frequency. And then using the information I have about the mass of the central black hole, I can convert these constraints into constraints on the mass ratio as a function of frequency. An interesting thing is because of the shape of the sensitivity curve of nanograv, it turns out that above a critical frequency, the constraints we are placing are independent of frequency. So this is practically flat and extends to higher frequency. So we repeated the same analysis for the entire population. And here I'm showing the mass ratio constraints as the color, as a function of the distance and the black hole mass. So as it is obvious here, for several of the galaxies, we can place very significant constraints. So if there is a binary there, the mass ratio has to be very low, less than 10%, which is comparable to a binary in the constraints we place on a binary in the Milky Way.